So let's take a look at another definition here to kind of add to the list of definitions we have thus far. A subset of a sample space is called an event. Now by a subset, we just mean a few of the options or some of the options from this sample space that we have up here. So if I select just a couple of these, then I refer to that as a subset. So that is what we refer to as an event. So events are often going to be denoted by letters. It's just for a way to create like a shorthand for us to use as we work through different problems. So for example, in problem number 1, a possible event could have been the spinner lands on the color blue, right? I mean, that's one of the different options that comes out of my sample space. So that's an event. And I could abbreviate that statement with a letter, maybe the letter A. Maybe I come up with a different event. The spinner lands on a non-primary color. Remember that our primary colors are what? Red, yellow, blue. So I could see here then that the colors that are not red, yellow, or blue would be like pink, green, orange, gray. And so I can kind of get all of those summarized with an event that I could call B. Now when we ask or talk about the probability that an event A will occur, we're going to denote that by using this notation. Much like function notation in an algebra class, where we have P stands for probability, and then I'm going to find the probability of A, where A is the spinner lands on the color blue. So I would actually read that, the probability of A actually occurring. Now, once I start to define this sort of notation, there's a couple other important things that we have to make sure that we understand. The probability of an event is often, or is this kind of the same thing as like the likelihood of an event occurring by chance. And it's always therefore going to be a number that exists between 1 and 0, inclusive, meaning that it could be exactly 0, it could be exactly 1, which measures ultimately how likely it is that an event will occur. So a couple quick rules then that come up that are very important for us is that for any event that we have, when I measure the probability of that event, it's got to be somewhere between 0 and 1, could be equal to those values. But also, when we say here we want to measure the probability of S, that is, I want to measure the probability that something in the sample space occurs, that probability always must be 1. And if you think about it, that should make a lot of sense. If I spin that spinner that we looked at previously, what are the chances that it's going to land on one of these colors? Well, it should be 1 or 100% because there were no other colors. So it's important that this is something that we have in place when we look at different probability experiments. This has to be true in order for us to have what we would call a valid probability model. Now, one other thing to keep in mind here is that if all outcomes of an experiment have the same probability of occurring, then the outcomes are said to be equally likely outcomes. So if we were to go back and take a look at the spinner, we can see here that, yeah, my different sections of the circle are kind of all the same size. And so there's the same chance of landing in gray as there is in landing in blue. These events would be called equally likely, or they'd be equally likely outcomes. However, it's not always the case that things are equally likely. If there are 3 possible outcomes to a probability experiment, the probabilities of them are not necessarily each 1/3. That's a really tempting thing to see. It's one thing to see here that, oh, it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers here. So does each one of those have the same chance of occurring? No, they definitely do not. We'll see more about why that's the case down here in some later sections. But I can even see up here with spinning the colors that at first glance, yeah, this would be equally likely, but all it would take is for me to just drastically change the size of one of the portions, and now, is it the same chance to spin every color? No, I mean, I can easily see here spinning and landing on pink is going to be like unbelievably difficult to do, not very likely at all. So it's not the case that I always have equally likely events. I got to be careful about this and really think about if equally likely events are the case in the experiments that I'm working in. So let's take a look here at example number 2. We want to go ahead and consider an experiment where we roll a 6-sided die one time. And we're going to try to answer some questions associated with this. We'll start with a rather simple one. If I was interested in what number I was going to roll, I could ask, what is the sample space for that experiment? Well, if I'm rolling a 6-sided die, then the only numbers that I could possibly roll would be 1, 2, 3, 4, 5, or 6. Those are the only possible outcomes for the experiment. Now I could start to go ahead and I could ask some different questions here, like, let's see, how about the event O occurs whenever the number rolled on my die is odd? You can see here that I might have chosen O as my representative letter just because it makes me remember the word odd, and oftentimes it's how we'll choose letters. So I want to write the set of outcomes that represents the event O. Let's do that first. So if O occurs whenever I roll an odd number, then what are the different possible outcomes up here that would make O actually happen? Well, that would be like rolling a 1, a 3, or a 5, since those are my only odd number values. So now I could ask, what's the probability that O occurs? So notice I'd write that like this. P, the probability that O occurs. And all of this will become equal to some final value. Now interestingly here, what I can see is that on a die, if this isn't a trick die, if it's not like weighted to land on certain numbers more likely than others, then I would have events here that are going to be equally likely. And in that case, I can easily see that there are 3 different odd numbers out of a total of 6 possible options. And since they're equally likely, I can compute my likelihood in this way. So the probability of getting an odd is 50% chance. Take a look at the event M. M occurs whenever the number rolled is at least 3. So notice that means 3 or larger, because 3 is the least number that you can roll. So what would be the items that make up the event M? Well, if 3 is the least, then I could do 3, 4, 5, or 6. So notice, then if I wanted to find the probability of M, since again I have equally likely outcomes when I roll a die here, I'm going to end up with 4 options out of 6, which gives me roughly a 0.6667, or a 66.67% chance. So this kind of demonstrates how I could actually go ahead and start to loosely measure probabilities if I had simple, equally likely outcomes.